In part C, we have cotangent squared theta minus cosine squared theta equals cotangent squared theta times cosine squared theta. So that almost seems unbelievable, doesn't it? That when we subtract these two functions, we get the same exact result as if we multiply those two functions together for the same angle theta, of course, plugging in theta to all four places. So we want to prove that this is true. I think, well, maybe it's not exactly obvious which side to start with, but if you look at this side, I'm going to explain why I'm going to pick the left side. This is cosine squared theta over sine squared theta, and then times cosine squared theta. So I just get 4 powers of cosine in the numerator and 1 or 2 powers of sine in the denominator. Maybe not real obvious where to go from there. But if I pick this side, because of the two terms, I can get a common denominator. So I'm actually going to pick this side. So on the left-hand side, I'm going to rewrite that in terms of sines and cosines as well. So cotangent squared theta is cosine squared theta over sine squared theta minus cosine squared theta. The lowest common denominator there is, of course, sine squared theta. So I'm going to use that. And then write that as one fraction with the denominator sine squared theta. So we've got cosine squared theta minus cosine squared theta sine squared theta. And then notice cosine squared theta is common to both terms, so I'm going to factor that out. So when I take that out, I'm left with a 1 in the first term, and then minus sine squared theta in the second term. All right, so now here's the one that shows up a lot, the 1 minus sine squared theta or 1 minus cosine squared theta. That's our fundamental identity, Pythagorean identity, and that this is equal to cosine squared theta. We got cosine squared theta times cosine squared theta over sine squared theta. And if you go back up here, notice that's what we had for this expression. This is cotangent squared theta, and then we still have the cosine squared theta. So now we've completed the proof. So if you had started on this side, I did kind of start on that side, you can still complete the proof. You're going to have to go from here to here and then make this replacement, which is, once you get used to it, not so hard to think about that, but maybe when you're first starting out, that's not the most obvious thing to do. So this, you start with the left-hand side and you show it equals the right. Well, then the right-hand side, if you start with that, you just go the reverse direction to show it equals the left, since everything's equal. All right, part D. Okay, so on this side, everything's in sines and cosines. You can't, there's not, not two fractions to add up. You can't split this up into two fractions because there's only one term in the numerator. So you might want to start with the right-hand side this time. Because that side we can write in terms of sines and cosines. Oh, I should mention the 2u here, don't be confused by that. That just means the input, is 2u, double u, instead of just u. You just have to write 2u in every expression. It doesn't change how you do the problem. So cosecant of 2u is 1 over sine 2u. Cotangent of 2u would be cosine 2u over sine 2u. And notice this already has a common denominator, so this is 1 plus cosine 2u over sine 2u. And then, well, this is, you could split this up into two fractions, so let's try that. Oh wait, why would I try that? What am I thinking here? That's how I got here. That's silly. Need more coffee this morning. All right, that would, yeah, that's how we got there. So no, that's not going to work. So at this point, it's not real obvious where to go. So now I'm going to show you another technique here that we haven't talked about yet. So if you look at these two sides, they look almost kind of similar. Notice the sine 2u is in the other place, and these two are what we call conjugates, right? We got a number or an expression minus an expression, and then this is expression plus an expression. So these are similar, but they're conjugates. So what we can do is, and maybe I'm going to use this one to just show you, like, okay, I'm going to stop here. I'm not sure what to do. Now I'm going to take the other side. So I start with the left-hand side. And I say, okay, I'm going to take this, and I know there's really nothing to do here, but I see this 1 minus cosine 2u. What if I multiply this times, again, a fraction that equals 1, but I use this conjugate, 1 plus cosine 2u. 1 plus cosine 2u. And that, the real hint to do this is because I saw this. But also, if you don't see anything else to do, this is a technique you can try. So what happens when you use this technique is, because these are conjugates, and you can do this, sorry, let me start over. We could do it to this one, we would multiply times 1 minus cosine 2u over 1 minus cosine 2u, because that is a conjugate here. So it doesn't have to be in the denominator, it can happen in the numerator, okay? So what happens in the denominator here is when you distribute, the outside and inside terms cancel, right? So you just get 1 times 1 is 1 minus cosine squared 2u, and that's helpful because you can use that Pythagorean identity. If I had used this one, we'd get the same thing in the top, and again use the Pythagorean identity. So in the numerator we have sine 2u times 1 plus cosine 2u. I'm leaving that factored because I want, if I'm looking at, let's scribble this out. I stopped here. If I'm looking at this, that's what I want up there, so I'm going to leave it factored out. So now 1 minus cosine 2u, let me write the top down first, is sine squared 2u, using the Pythagorean identity. And then notice one of these cancels. And because I've now got to this, I can really stop. That equals, star. Because once I get that, I can just complete the proof going backwards. So if you stopped here, it'd be okay with that as long as you reference this, because this equals the right-hand side. But if you wanted to write it all down, you could just put these steps in reverse order. So, this now split up into two, like I was talking about before, but of course that would be silly because that's how I got there. But this is 1 over sine 2u, I'll just put this in parentheses, plus cosine 2u over sine 2u, which equals cosecant 2u plus cotangent 2u, and then we're done. So that on the first page there, when I was talking about step 2, transform separately and you get the same expression. The identity is proven because that same expression, you could just complete the proof by going backwards on one of the steps. Or we could take this side and then go this this path to complete the proof up here. Either way. All right, let's do the last one. E has a real clear cut side to start on, and there's lots going on here, and this is just 2 secant x. So I'm going to start on the left hand side. And I think I wouldn't change to sines and cosines yet because I've got 2 separate fractions. I'm going to combine those first. And then I'll think about if I need to switch to sines and cosines. So the first fraction, well, the LCD here would be 1 plus cosecant x times cotangent x. So the first fraction, I need to multiply by cotangent x over cotangent x. And then the second fraction, I need to bring in the 1 plus cosecant x. So I'll use 1 plus cosecant x over 1 plus cosecant x. Okay, and we're going to have to do some distributing up here. All right, so I'm going to put this all over. Now my common denominator, right, if I add these up, is cotangent x times 1 plus cosecant x. I would just leave that factored because we're hoping something will cancel. And if you distribute, then you might have to just refactor it. So I'd leave it in factored form for now. Cotangent x times cotangent x is cotangent squared x. And then up here, taking this 1 plus cosecant x times itself, we're going to have to distribute all that. So 1 times 1 is 1. And this is a plus, which is nice, so we can keep all of our signs. Then the outside 2 give me cosecant x, and the inside 2 give me cosecant x. So I get plus 2 cosecant x plus cosecant x times cosecant x is cosecant squared x. All right. So the top looks pretty complicated, but this here is an expression in one of the Pythagorean identities. That cotangent squared x plus 1 is cosecant squared x. And that is nice because there's lots of cosecant x's up here, so I get, these two are like terms. So I've got 2 of these. Whoops. 2 cosecant squared x plus 2 cosecant x over cotangent x times 1 plus cosecant x. Kind of running out of room. I'm going to write smaller. So now from here, notice that 2 cosecant x is common to both. And I'm happy to get this 2 in here because if you look back where I want to be, there's a 2. So that's good news. So factor out the 2 cosecant x. And then we're left behind with cosecant x plus 1. And these are the same terms, or factors. Not terms, they're factors. They're the same, so we can cancel them out. We've got 2 cosecant x over cotangent x. So let's rewrite that. Cosecant x is 1 over, I don't have to write the 1. I've got a 2 up there. Let's leave it as a 2. But that's 1 over sine x, so sine x in the denominator. And then cotangent x is, you could bring it up as just tangent x, but tangent x is sine x over cosine x. So these cancel. 2 over cosine x is 2 secant x, which is exactly what I was trying to show. So I'm done with the proof. Right, that's our right hand side. Okay, well it does take some practice, and you need to be careful again about making sure you've got all the variables in your functions, that each expression is equal to the one before. If you're finding common denominators, that you're multiplying by unit fractions, right? Not just writing cotangent x here, but cotangent x over itself, etc. It's important that you practice some that aren't just in your online homework, because the online homework kind of leads you through it. It's hard to do these problems using computer-based homework. So you want to practice some where you have to come up with the steps all on your own. And of course there'll be some on your worksheet to give you some more practice besides just on the computer, because that's not what's going to happen on your test, of course. So you want to make sure you're practicing for your test. All right, well, let me know if you have any questions, or if you get stuck on any as you're working through them. Lots of examples in your textbook to practice with paper and pencil. So you should look there for some examples.